Okay, so acids and bases. Last week we talked about solutions. Acids and bases take place in solutions, so this is building on that knowledge. Oh, the other thing I wanted to say, unfortunately this will be in the recording now, is that I'm going to kind of try and skip over some of this other stuff because we are very behind. Still, we need to catch up. So some of this stuff will go fast through. If I go fast through it, that means it's not going to be on an exam. You don't need to worry about knowing it. So things like this, acids are found in a lot of foods. We see acids in like movies and stuff as like a vat that will dissolve you or anything you throw into it. Most of the time, it's not the case, right? Sometimes it's delicious, like Sour Patch Kids. Acids combined with your saliva produce hydrogen ions, and those ion molecules, or ions, react with proteins in your tongue and send electrical signals that you experience as sour. So this is a concept that we're going to use a bunch. The H plus is just a proton because a hydrogen is a proton and electron. If you take away the electron, then it's H plus. So some of the basic properties of acids: they have a sour taste, they dissolve many metals, and they turn blue litmus paper red. Yeah, so like citric acid in lemons and limes, very sour. These are some examples of acid formulas and kind of the stuff that they're used for. We've looked at how to name acids. So you think hydrochloric acid, sulfuric acid, nitric acid, used for anything from cleaning metals to food preparation. Hydrochloric acid is actually the main component of stomach acid. You can zoom a little bit here. Other things are used for fertilizers and explosive manufacturing, plastic, rubber, a lot of different things. Bases, in some ways, are the opposites, in some ways, the opposite of acids. If you think of bitter as the opposite of sour, there's a reason the bases are bitter. They have a slippery feel, and they turn red litmus paper blue. We actually used some red litmus paper for one of the labs. This is red, although the screen doesn't show it. For the most part, cleaning products are the bases that we use all the time. Drano is actually, I think it's sodium hydroxide, but it might be potassium hydroxide. And potassium hydroxide, sodium hydroxide bases are really good at dissolving things like hair that gets clogged in drains. They feel slippery because they react with oils on your skin to form soap-like substances. They're less common in foods because a lot of toxic plants produce bases, and those bases are toxic. So it's kind of like our brain saying, like, hey, don't eat that. It tastes bad because it's poisonous. Not all bases are poisonous. For example, caffeine is actually a base, which imparts that part of the bitter flavor of coffee. But most Americans consume caffeine on a regular basis. Have some right now. Oh, just a drop. Some bases, we've seen these before. I'm sure you've seen them in problems, homework problems. Sodium hydroxide is a base. Notice that the common theme, I guess for just two of these, is the presence of hydroxide as a part of the chemical formula. So hydroxides are bases. We have other kinds of bases that don't have hydroxides in them but form them indirectly. We'll get to that. All right, here's an important slide. So we're going to have two definitions of acids and bases. This is the first one, the Arrhenius Definition. Main takeaway here is the definition of an acid in the Arrhenius definition is that it produces protons, or H plus ions, in aqueous solution. So hydrochloric acid by itself is a covalent compound. The hydrogen's bound to the chlorine, but when you add it to water, you produce the ions H plus and Cl minus. So because when you add this to the water, it makes H plus, it's an acid. Arrhenius definition, if it makes H plus, it's an acid. Pretty simple. The hydrogen ions are highly reactive. This is less important, but in chemistry, we'll often write just this H plus. In reality, that doesn't exist. There's no H plus by itself in water. It's always going to find a water molecule and attach itself so that we get H3O plus. So this is H3O plus. And that's hydronium. So while this is the reality, they get used interchangeably. So you'll see H plus and H3O plus, they both mean the same thing, that there's a proton in the solution. You should know this, hopefully, from nomenclature. For acids, the hydrogen that's written first, that is one of the ways I told you to identify an acid, that is the hydrogen that leaves when you add it to a solution. So something like hydrochloric acid, HCl, right? The hydrogen's first, that's the hydrogen that leaves. This is a more important note for organic compounds. So formic acid here is HCHO2. Only one of those hydrogens leaves. More of just a note. It won't come up very often in this class. Bases, on the other hand, under the Arrhenius definition, and again, this is one of those important things to write down, a base produces OH minus ions in aqueous solutions. So sodium hydroxide is an Arrhenius base because it dissociates into a sodium plus and an OH minus when you add it to water. So bases produce OH minus ions. If you add sodium hydroxide to water, the sodium and the hydroxide split. It's an Arrhenius base. This is really only the case for inorganic or metals with hydroxides. Something like CH3OH. This hydroxide, or this looks like a hydroxide, is not a hydroxide. This is methanol. It is not a base. Under our Arrhenius definition of acids and bases, this is one of the reasons that I said that acids and bases are sort of opposites. They cancel each other out when you add both of them to water. So under Arrhenius definition, right, so an acid adds protons, a base adds hydroxides. If you combine those two things together, you get water. And so we've seen this reaction before as an acid-base neutralization reaction. We hadn't talked about what acids or bases were yet. There are, though, some things that act like bases that don't put OH minus directly into the solution, which is why we need another definition. But also real quick, I forgot, I have another, I saved a bunch of these. Also, you remember I was talking about atoms in any state above 0 Kelvin are moving. They're grooving. So, I went crazy on this. This is one that comes up. This is going to go early on. So the best things about r/chemistry memes, I think, is that you read the meme and then you're like, wait, why is this funny? And then you go and you figure it out. And oh, I love this one. Methanol, ethanol, espanol. Okay, I'm going to find this one. Oh, yeah, here we go. It's Thanos. It's hard to see. I use the water to destroy the water. So take two water molecules. We'll talk about autoionization here, too. But that's your H3O plus. That's the hydrogen, hydronium, and then the OH minus. So Yeah, this is called autoionization. All right. So we take our acid, take the base, combine them together, they make water. But this isn't a perfect definition, which is why we have more than one. So it's time to learn a new definition of acids and bases. The Brønsted-Lowry definition has only slightly different definitions. Remember, H plus equals a proton. So an acid is a proton donor. So in our Arrhenius definition, an acid was anything that added H plus to the solution. So adding H plus, adding a proton, acids are the same for the Brønsted-Lowry definition and the Arrhenius definition. The thing that changes is that a base is a proton acceptor. So we've kind of thrown out this idea of using OH minus, because it's not just OH minus. There are other types of proton acceptors. But draw this one out again, right? H plus OH minus gives you water. So OH minus is a proton acceptor, right? It takes this proton, becomes water. So the Brønsted-Lowry definition covers the Arrhenius definition, but there are some gaps. And actually, an analogy I thought of is that it's like, I should have gotten a picture of this. You know, like the little kid's play toy, right? Where it's got like the different holes and the different pegs. But you can usually fit all of the other pegs through the square hole. So this is like the Arrhenius definition is like putting the round peg through the square hole. It covers a lot of it, but not everything. So this is like the square peg for the square hole. The focus is on where hydronium or protons or hydrogen ions are going. So going back to hydrochloric acid, again, it's an acid because it's donating its hydrogen, donating its hydrogen to the water. So because it's donating, it's an acid. So this definition's better for talking about what happens to the H plus ion in that we're transferring it from the acid to the base. And so under the Brønsted-Lowry definition, we're always going to, if we have an acid, we are going to have a base. They come in pairs. Switching over to bases again, the Brønsted-Lowry definition works well with bases like ammonia, because other bases that we mentioned before, like sodium hydroxide or calcium hydroxide, those have OH minus ions, hydroxide ions, so you can see those. But ammonia acts like a base even though it doesn't have hydroxide as a part of it. And that's because when you add it into water, it takes a hydrogen from water, from one of the water molecules, forms NH4 plus, and then an OH minus ion. And by the Brønsted-Lowry definition, it is a proton acceptor, which is a base. As I just mentioned, our acids and bases, right? Proton donor, proton acceptor will always occur together. Because to be a proton donor, you have to donate it to something. You can't just get rid of it. We talked about protons are highly reactive in solution, or just highly reactive, really. And usually, water is either the acid or the base. It's a special type of substance, or special category of acids and bases. It's called amphoteric. So it can act as an acid or a base, depending on if it's accepting or donating a proton. So for this first one, we have our hydrochloric acid. That proton gets donated to water, and we get H3O+. if we have ammonia, now water is donating one of its protons to the ammonia to make ammonium. And so water here is acting as the acid. So the other term that we're going to throw in here is a conjugate acid or a conjugate base. So this is our ammonia plus water reaction from before, but now we've reversed it. So instead of going from ammonia to ammonium, we're going the opposite direction from ammonium to ammonia. All right, so this one has 4 hydrogens, this one has 3. So this is called a conjugate. Conjugate means like locked together or comes together. It's called a conjugate acid-base pair because one of them acts as the base, the other one acts as an acid. And really the differentiator here is going to be which one's on the reactant side and which one's on the product side. So here, this is our acid. That's a proton donor. So its conjugate base is the ammonia on the product side. If we write this going the other direction, NH3 plus H2O, NH4 plus OH minus, right? So took that reaction and wrote it the other way. Now NH3 plus is a base, and NH4 plus is its conjugate acid. So it all just depends on which way the proton's going. The reactant side is always going to be your acid or your base. The product side will be a conjugate acid or a conjugate base. All right, so our conjugate acid-base pair, any two substances related to each other by the transfer of a proton. So I could ask the question, you know, what is the conjugate base of HCl? So conjugate base of HCl, if this is, so maybe this is not an excellently worded question, but we're asking what the conjugate base is, so that implies that HCl here is an acid, which you should also know because it's got a hydrogen first. So if we take the hydrogen away from HCl, what are we left with? Cl minus. So Cl minus would be the conjugate base of HCl. And then you could ask the reverse question, what is the conjugate acid of Cl minus? So you just add a proton to it. It would be HCl. Yeah. Any questions on that? This is one of those lectures where the terminology, I think, is really a sticking point. Digesting the definitions of acids and bases. Okay, so a base accepts a proton and becomes a conjugate acid. An acid donates a proton, becomes a conjugate base. So here, again, NH3 takes one of these hydrogens, becomes NH4 plus, so that's the conjugate acid. Because if we took this and wrote it backwards, going the other way, then NH4 is donating to OH minus to become NH3. All right. So for each of these, we're going to identify the Brønsted-Lowry acid, the Brønsted-Lowry base, then the conjugate acid, conjugate base. So I think a good analogy for these is like a spot the difference thing, right? Where it's two pictures and you have to find the differences. So here we're looking for what's gaining a proton and what's losing a proton. So for A, which of these, let's do we'll do the base first. Which one's gaining a proton? We go from left to right. So C5H5N, and then on this side we have C5H5, C5H5NH+. So it's got one more hydrogen on this side than it had on this side. So that means it accepted a hydrogen. So this will be our base. So what's our acid? So H2O here would be our acid. I don't know why I'm writing H2O. This is the acid. Because going from left to right, you could do these in either order, but here we have H2O, and if we look on the other side, now we have OH minus. So it has one fewer proton. And then we just line up the base with its conjugate acid, because if this is the base, the version of that in the products with one more proton is our conjugate acid. And then for our acid, we just, again, line it up with its pair. And at this point, you can just say, use the process of elimination. So this is our conjugate base. All right. So for B, which of these is our acid? Now, the acid is the proton donor. So it's the one that loses a proton when you go from left to right. And I can do, here, I'll zoom this, and I'll even do this. 1, 2, 3, 4. So you don't have to worry about trying to remember the nomenclature. So which one is the acid? It's the one that donates a proton. So it'll have one fewer proton on the other side. Yeah, one. So HNO3. Because here we have one more proton than we do on the opposite side. So this is our acid. So which one's our base? H2O would be our base. And then our conjugate acid will be the opposite, well, paired with, but opposite the acid. Did you say that right? I think I said that right. Our conjugate base. And then this will be conjugate acid. Any questions? Yeah.
So when you know it's a conjugate base or acid, it's just like the opposite.
Mm-hmm. Yeah. And the conjugate base, conjugate acid are always going to be the products. And then the acid and base will always be the reactants. This is one of those things you heard from some people that the balancing problem that we did last week on Wednesday was a lot easier than the first time we did balancing. So this is one of those things where it might take a little time to digest these definitions so that your brain can use them readily. But that's why there's homework, because those are the problems to practice these things. So our neutralization reactions, acid-base neutralization reactions, generally form water and a salt. Not just salt, not just sodium chloride. A salt is a metal cation and a nonmetal anion. So they're all ionic compounds. Right, or salt and ionic compound. So, right, acid plus a base. The hydrogen from the acid plus the OH minus from the base becomes the water. And then our salt is made up of the conjugate base of the acid, or here with the anion, and then potassium's coming from the conjugate acid of the base. Or really, the salt is made up of what's left. Right, so once you've taken the hydrogen and the hydroxide, all you have left is Cl minus and K plus, and that becomes the salt. If you remember net ionic equations and complete ionic equations, that's where we took these and broke them into their individual ions. And then again, like a spot the difference puzzle game, the stuff that is the same on both sides cancels out. And so when you do that for an acid-base neutralization reaction, you get this left over, because the only thing that's actually doing anything is the H plus reacting with the OH minus to make water. Because, actually, I can do this. So the complete ionic equation for this would look like H plus Cl minus plus K plus OH minus. And we would get H2O, because it's not an ionic compound, plus K plus Cl minus. So on the left side of our equation, Cl minus, K plus, K plus. All right, so those things are the same on both sides. So it means that they haven't changed at all. They haven't actually reacted. They're not part of the equation. And all that we're left with is H plus, OH minus, and H2O that actually participate in some kind of reaction. All right, so that matches what's written down here. All right. This acid-base neutralization reaction is what we do in titrations. Hopefully we get to that today. Some other reactions, one of the ones that, have we done it actually in lab? Is a reaction of HCl and sodium bicarbonate. So sodium bicarbonate, I'm trying to think, you guys should have bottles of sodium bicarbonate on the benches, but you might not. Essentially, whenever you spill any acid, you're supposed to use sodium bicarbonate to clean it up, because it goes through this reaction down here, and the hydrochloric acid will react with the sodium bicarbonate, and you're left with water, CO2 gas, that's why it bubbles and fizzes, and a salt, sodium chloride. So it takes the acid, which could be dangerous if it's concentrated enough, and turns it into harmless compounds. And we saw this is one of the gas evolution reactions that we looked at way back in like chapter 6. All right, so you're going to write out an equation for these. See what I want to say about this. We're given here the starting reactants in the word problem. So write a molecular equation for the reaction that occurs between aqueous H3PO4 and aqueous sodium hydroxide. So, right, this is the reaction between this and this. So we write out this molecular equation. That's where you should start. H3PO4 plus sodium hydroxide. And then our products, because this is an acid-base neutralization reaction, is going to be water and a salt. And actually, this will be a good time to do this too. So we can use a complete ionic equation to help identify how things are going to mix up. So we're going to have 3H plus PO4 3 minus plus Na plus OH minus. So those are all of our ions that we have in the solution. And I did the 3 from the hydrogens is why we have 3 there. Okay, so since it's an acid-base neutralization reaction, the hydrogen is going to react with the OH minus. And we're going to get H2O. And then we're also going to have, since this is the complete ionic equation, we're just writing out all of the ions, Na plus and PO4 3 minus. So then for our molecular equation, so this is the molecular equation, and this is the complete ionic equation. We get H2O plus, and now we need 3 of these sodiums, because we're going to combine these 2 together. So we're going to need 3 sodiums for the phosphate so that the charges balance. So Na3PO4 and we know that we're going to have to add, so because this required 3, now we kind of work backwards and say, oh, we need 3 NAs. But we could also just balance our molecular equation here. So I wouldn't start with hydrogen because we have hydrogens in 2 separate places. We can start instead, you could look at phosphate. Again, phosphate, there's 1 there, there's 1 here. Sodium, so that we don't need to do anything with phosphate. For sodium, there's 1 over here, and there were 3 over here. So we had that 3, now there's 3 of those. That means that we have 3 oxygens. So we need a 3 there for water, so we have the right number of oxygens. And now if we look at hydrogen, this is 3 times 2, so 6 hydrogens in the products, 3 times the hydrogens in hydroxide, and then 3 from phosphate. So that would be the answer for this. And here we're assuming that the H3PO4, which is triprotic, so it has 3 protons. That's why all 3 of those hydrogens are in front, because all 3 of those can be ionized or can come apart in solution like this. So for any of these acids that have more than 1 hydrogen up front, you're going to need that many hydroxides to react with all the hydrogens. So here we get a 3 hydroxides to react with the 3 hydrogens and give us 3 moles of water. Any questions there? It was a lot. This is a very, very mixed question. You don't need to do this, but I feel like it helps illustrate how we swap things around. So we're going to glaze over these pretty quickly. You can have acids can dissolve metals. Metals that dissolve all undergo similar reactions. The one that we did in class, I believe, was hydrochloric acid reacting with zinc to produce the hydrogen gas, which is what these do. So you have some acid reacts with a metal and then produces hydrogen gas, and again, a salt. So same thing for all of these. Some metals don't react. If you want to know more about that, it's in chapter 16. It's called the activity series. So when you do this, if you remember that whole little zinc strip that we put in the glass tube called a eudiometer dissolved. So when metals react with acids, they do so in a way that lets them dissolve into the solution and produce gas. You can also have reactions with metal oxides, which are very similar, but instead of getting H2 gas, we get water instead. So the oxides from the metal, or the oxygen from the metal, combines with those two hydrogens from the acid to form water. So just very quickly, again, this is the kind of problem where you really need to know the nomenclature. So hydrochloric acid, to break this down, the hydro here tells us that it's a binary acid. And then chloric tells us that it's a binary acid of chlorine. So that means it's going to be HCl. And then strontium metal is just going to be Sr. So because this is a reaction with just a metal and not a metal oxide, the products are going to be H2 gas plus SrCl2. And then if we wanted to balance this, 2 goes there. So we know that it's going to be SrCl2. We know that there's 2 chlorines because strontium has a 2+ charge. Chlorine has a 1- charge. So 2 chlorines to balance the charge on strontium. And also, that's what's left. We'll have strontium and chloride left. The key for this kind of problem is knowing that you're going to produce hydrogen gas. And then the other stuff has to combine to make the salt. Okay, so this next one, again, we have hydroiodic acid. So hydro tells us again that it's a binary acid. Iodic tells us that it's a binary acid of iodine. So just like hydrochloric acid is HCl, hydroiodic is Hi, plus barium oxide. So barium is Ba, oxygen is O. And then the charge on barium is always 2+, charge on oxygen is always 2-. So we just need 1 barium, 1 oxygen. That balances their charge. Now, because we're reacting with an oxide here, we're not going to produce hydrogen gas, but instead we're going to have water, H2O, plus barium iodide. Don't worry too much about these. Again, like with the acid reactions, just going to kind of glaze over these. The most important base reactions are neutralization reactions. Those are the ones we talked about. That's acid plus base. There aren't many reactions that with hydroxide. Aluminum is one of them. Just take a look at it here. Again, these aren't going to be on the exam. All right, this is going to be on the exam, and this is one of the very key pieces of this acid-base chapter. And here we're talking about stoichiometry again. So solution stoichiometry, that's usually molarity and volume, then calculating moles of A to moles of B. The key part for solution stoichiometry is that we're using concentration and volume to calculate the number of moles. When it comes to acid and bases, this is called a titration. So titration is where we use a concentration of a known acid or base. It doesn't even have to be an acid or base, actually. But we use a known concentration of some solution, and we add it to a solution of unknown concentration, knowing that some reaction is going to take place. And then we have some method of identifying when we've used the same amount of moles of our known concentration as our unknown concentration. The net ionic equation, and the one we're going to use for the lab today, is going to be this H plus OH minus equals water. So for these acid-base neutralization titrations, we have a way to tell when we've used up all the hydrogen or we've used up all the hydroxide. So we're going to use these cartoon representations. So this is a hydrochloric acid solution. And here we're only showing the hydrogen ions, right? And we're only going to be showing in these the hydrogen and hydroxide ions because those are the only things that actually do anything in them. All right, so in this case, we have a solution of known concentration of hydroxide, made with sodium or potassium hydroxide, and an unknown concentration of H plus in our flask. So this is our hydroxide up here. We know exactly the concentration of that, and we use a burette. Have we used burettes yet? I feel like we did. We used them for something. So this lets us measure exactly how much of the hydroxide we're adding. Then at the equivalence point, so that's when we've added as many hydroxides to the solution as there are hydrogens in the solution. The solution turns pink because we use a special indicator called phenolphthalein. So that's what's happening here. So what you will be doing today, if you have lab today, a little higher there, is taking a burette of a known concentration of hydroxide, and you'll add drops of that liquid into your flask. And as you're adding those drops of that liquid, you're adding hydroxide molecules. Those hydroxide molecules go in and they find all of the hydrogens, and they react with them to form water. So your end point, the solution turns pink when you've added the same number of hydroxides from up here as the number of hydrogens in your flask. So our titration is usually, the equivalence point, this is one of the keywords, this should be bold. The equivalence point is signaled by an indicator which depends on the acidity of the solution. So how many hydrogens are in that solution. Usually one of the concentration of one of the reactant solutions is unknown, and the concentration of the other is precisely known. And so by carefully measuring the volume, I don't like this slide, we're going to skip it because it's way too wordy. Sodium hydroxide added to HCl. And then when these things reach stoichiometric proportions, or when they're exactly the same, then the solution changes to pink. So it'll be colorless, and then when you reach the end point, it'll be pink. As you're mixing it, it'll look like this, where you'll have like a swirl of pink and then it'll disappear. As you get closer and closer to the end point, there are fewer and fewer hydrogens, and so the hydroxides take a little longer to find them and actually react. So this whole process, the analogy that I came up with at COS last week when I did this lecture is, let's say that you've got cupcakes, and you've got to ice all these cupcakes, but you have to ice 3 trillion cupcakes, and you don't want to count to 3 trillion. You'll probably lose count, but you have a very handy dispenser of frosting, right? So this dispenser of frosting, you can measure exactly how much frosting you've used. It's got a special nozzle on it, so you only ever use 1 tablespoon of frosting for every cupcake. So you can frost cupcakes until you've finished them all, and then use the amount of frosting that you've used up to count how many cupcakes you used. So let's say that you start with, maybe 1 trillion was too big. Let's say you start with 100, let's call it ounces. Start with 100 ounces of frosting. Use it, use it, use it, use it. When you get to the bottom, now you only have 20 ounces of frosting left. Every cupcake uses 1 ounce of frosting. How many cupcakes have you frosted? 80, right? 100 minus 20 used 80 ounces of frosting. So all we're doing here is saying, okay, we have this many molecules of hydroxide, and we're frosting the protons in the solution with hydroxides. So if we can count how many hydroxides we used, then we can count how many, or know how many hydrogens we neutralized. It's not a great analogy. So the titration of a 20 ml sample of a sulfuric acid solution of unknown concentration requires 22.87 milliliters of 0.158 molar potassium hydroxide solution to reach the equivalence point. What is the concentration of the unknown hydroxide solution? So let's figure out what we're working with here in terms of numbers. So we have 20 mils of sulfuric acid. So I'm just going to write these over here. 20.0 milliliters H2SO4. And that's a solution of unknown concentration. So we can write question mark, capital M is molarity or molar. That's moles per liter. Don't know what the concentration of that solution is. H2SO4. Here we go. And then that required 22.87 milliliters of 0.158 molar potassium hydroxide. Okay, so we used 22.87 milliliters KOH with a concentration of 0.158 molar KOH. All right, so we've kind of distilled down this entire word problem to these 4 numbers. So if we just think about this in terms of hydrogens and hydroxides, neutralizing them, how many hydroxide molecules did we use? It's probably, the question is probably, okay, so this is a concept that we haven't talked about in a long time. What is a mole, like conceptually? It's okay. We haven't talked about this in a long time. A mole is a number of something. So we use it for atoms because atoms are so small that to have any like visible amount of them is too big a number. right? So 1 mole, say 1 mole is, that's the 6.022 times 10 to the 23. So the moles is the number of hydroxides that we've used. So how do we find the moles of hydroxide that we used? If we have molarity, that's moles per liter, and we have the milliliters of potassium hydroxide. So I'll convert the potassium hydroxide, 22.87 liters of KOH. So how do we find the number of moles of potassium hydroxide?
Convert it using Avogadro's number?
Well, convert what? What would we start with? How would we convert it?
Would use the molarity formula.
Uh-huh.
Then from there you would go from moles to Avogadro's number, but technically
We don't actually need, we don't actually need to go to Avogadro's number, but yeah. You're in the right track. So molarity is moles per liter. It's a conversion factor. So if we have 0.02287 liters of KOH, we can use the molarity of potassium hydroxide to figure out how many moles. So 0.158, molarity is moles over liters. Okay, so then 0.02287 times 0.158. So this is 0.003613 moles KOH. So how many in this 0.03613? How many moles of hydroxide is that? If there's 1 hydroxide per potassium hydroxide,
is it 1 mole hydroxide?
it's 1 to 1, but it's the same number. So it's 0.003613 moles of hydroxide. This is kind of like wow, what would be a good analogy? Oh, like a hamburger, right? It's like if you had 100 hamburgers, complete hamburgers, how many hamburger patties do you have? Assuming that there's 1 per hamburger, it's 100 hamburger patties. So if there's 1 hydroxide for every potassium hydroxide, remember, moles is a number of something, so it's just the same. So this is 0.003613 moles OH minus. So how many moles of H plus were in the solution? Oops. We're going to do this problem twice. We're going to do it once this way, and then do it once with the regular stoichiometry. So how many moles of hydroxide have to react with how many moles of hydrogen to neutralize them? It's 1 to 1. Yeah.
So is it 0.03613?
Yep. So that means that if we had 0.003613 of hydroxide, that means that we had to react with 0.003613 moles H plus. How many ionizable hydrogens does H2SO4 have? How many hydrogens does it have in front? 2. Okay. So, whoops. So if we have this many moles of H plus and H2SO4, every H2SO4 has 2 of them. How many moles of H2SO4 produced this many moles of hydrogen?
Would you multiply by 2?
Divide by 2. And actually, here, let me write it out this way. So there's 2 moles H plus for every 1 mole H2SO4. So anytime you say, it's this many of this per that, that's a conversion factor. You can write it out as a fraction. So this is kind of like, if I said you had 100, if you had 100 top hamburger buns and 100 bottom hamburger buns, how many hamburgers can you make? Or maybe slices of bread is better? All right, so we take our number, divide it by 2. 0.0018, we'll call it 0.7 moles H2SO4. So then what is the concentration of our H2SO4 solution? We just use molarity. Yeah, so molarity is moles of something per liters of something. So we have moles of H2SO4, and we have milliliters of H2SO4. So I have to convert the milliliters to liters. So we divide that by 1,000, but we'll get 0.001807 moles H2SO4. I want to move this over. Move it over more. Whoa, 0.0200 liters. So now we have moles divided by liters. So divided by 0.02. And the answer is then 0.090 molar H2SO4. I think it should be 0.3 because of sig figs, but I ran out of space. 0.0903. Okay, so let's recap what we did here. First thing is just pull out all the numbers with their units. Super important to bring the units with it. And we look at them here. And the base understanding that you need to have here is that we're using as many moles of hydroxide as there is H plus in the solution. So we have the volume of our potassium hydroxide. We have the molarity of potassium hydroxide. So I converted the volume into liters. And then we used the molarity to calculate how many moles of potassium hydroxide we have. So that gave us this number. So that's how many moles of potassium hydroxide we had to add to use up all of the H plus in the solution. Then I asked you guys, okay, so if there's this many of potassium hydroxide, it's the same amount of OH minus hydroxide. So then this is the net ionic equation. So it's for every one hydrogen to neutralize, we need one hydroxide. So it meant that this number is the same as this number. The number of moles of hydroxide is, again, the same as the number of moles of H plus. So if we know the moles of H plus, and we know that all of those came from the sulfuric acid, then we can calculate using the 1 mole of sulfuric acid would give us 2 moles of H plus, and say that, okay, this number of moles of H plus would come from this many moles of sulfuric acid. And then to calculate molarity, we just take this number of moles, right, because molarity is moles divided by liters, and we divide it by the amount of solution that we had in liters to get the molarity of H2SO4. Any questions? This is the math for the lab. Okay, let me copy this slide again, and I'll go faster, but copy, paste. Okay, and then clear. All right, so we'll start it the same way. I'm going to do these conversions to liters up front. So this is 0.0200 liters H2SO4, unknown concentration H2SO4, 0.02287 liters of potassium hydroxide, the concentration of 0.158 molar potassium hydroxide. Okay. So when we set up a stoichiometry problem for this, it's not a straight line, but that's okay. Basically going to do the same thing, but we're not going to like stop and talk about all the steps in between. But this will be all of the same steps in a single line. So for almost every problem, you're going to start with the thing that's not a conversion factor. So we're going to start with the 0.02287 liters KOH, and we want to convert that into moles, right? We need to know how many moles of hydroxide there are. So that's going to be 0.158 molar KOH. Moles KOH, 1 liter KOH. And now, and this is kind of based on what we did before, but we know that for every KOH, we're going to get 1 OH minus. But for every H2SO4, we're going to have 2 hydrogens, 2 H plus. So we could write out the equation, KOH plus H2SO4 will give us H2O plus K2SO4, and then to balance this, this is more like the other stoichiometry problems we've done. And we say we want to go from moles of KOH to moles of H2SO4. So this is where that 1:2 ratio comes in. So for every 2 moles KOH, that'll neutralize 1 mole H2SO4. And that'll tell us the number of moles of H2SO4 we have. And then we'll just divide that by our number of liters H2SO4. It looks a little weird here at the end because we're not actually doing a conversion necessarily, but we're making the conversion factor. So we want it to be moles divided by liters. So we'll do 0.02287 times 0.158 divided by 2 divided by 0.02 gives us, and I never leave enough room, 0.090 molar H2SO4. And really, maybe I should have done more stuff like this when we were talking about other stoichiometry problems, but this is the same concept that's happening with those stoichiometry problems. We're calculating the number of moles of one of our things, and we say, okay, well, if we have this many, how many of the other thing can we react with? So you can see this is a much more compact and fast way to do these problems. And if you really want to, and what might be helpful, is to look at, from your notes or from the video, look at this slide, compare it to this slide, and try and match the math that we did here with each part of this way of doing it. Any questions on stoichiometry?
I have a question. For the bottom half, you said it was like a conversion factor. We used the 20.0 milliliters, right, under the for the H2SO4.
Yeah, I just converted it into liters.
Okay.
So you could have a step in here that converted it to liters, or I would recommend just doing that beforehand. Okay. Right. Yeah, I guess we'll stop there. And I think the pH worksheet, I need to go through and